Hello Global Oceans 2020. My name is Ole Lorentzen and I'm a PhD candidate at the University of Oslo and a scientist at the Norwegian Defence Research Establishment, or FFI, in Norway. Today I have the pleasure of presenting my paper on backscatter features for synthetic aperture sonar bathymetry. This work is together with my colleagues Torstein Sæbø and Hansen. Synthetic aperture sonar is a signal processing technique that improves the long track resolution of side scan by a coherent combination of pings. This yields very high resolution images while still maintaining a large area coverage rate. We can see details on a centimeter scale, such as small rocks or the shape of larger ones, and even photographic-like detail on man-made objects such as this shipwreck. Our system is the SASB 1032 on the Hugin AUV that FFI has developed in cooperation with Kongsberg. For our system, we have about 2 by 2 centimeters theoretical resolution and we maintain a coverage rate of about 2 square kilometers per hour. So this is the current state of the art for seafloor imaging, and it's currently in use by academia and industry and military users as well. All the simulations and the real data in this talk is for the SASB 1032 system. By coherently adding the signal from more and more pings into each pixel in our image, we are able to focus the image as if we had an aperture that spanned the entire length of those collected pings. We can also measure the bathymetry and even combine these into beautiful renders. SASB bathymetry has been adopted slower than SASB imaging, but it has been available to academia and military users for some time, and it's also now being adopted by industry. When doing SASB bathymetry or interferometry, this involves using the signal phase in order to estimate the very fine time difference of arrival of two vertically displaced receiver banks. To do this, we use the signal phase. However, the phase values have a high variance. Therefore, it's necessary to reduce this by doing complex averaging of nearby samples. Typically, this is done by square window averaging, just including a square region around the current sample of interest, and using those samples for averaging. The downside of this is that the effective spatial resolution of our bathymetry is reduced. The result is that edges appear smothered, and objects that are much smaller than the filter size can even more or less disappear. We suggest a method to mitigate this by using the backscatter image, which is available in high resolution, in order to make a smart selection of which samples to include. The correlation between the backscatter image and the bathymetry is of course something that can be questioned. However, in many cases we do have high correlation. For example, an upward slope on the seafloor will change the bathymetry, but also tilt the seafloor towards the sensor and give us an increased grazing angle. This will give us higher intensity in the backscatter image, since the grazing angle is one of the most significant factors for the backscatter strength. In many cases, the elevated objects are made from harder materials than the surrounding seafloor. An example of this is a rock sitting on a sedimented seafloor. These also produce higher backscatter values. There is also some research on using the backscatter image directly without an interferometer in order to estimate bathymetry. So from this we assume that there is some correlation between the backscatter image and the bathymetry, and we intend to exploit this. To make the images, we use a full beamwidth backpropagation algorithm with a flat focusing plane at the seafloor depth. Then we do straightforward difference to create the interferograms and estimate the bathymetry from these. Finally, we do geometric correction of the initial SASB image using the estimated bathymetry. This means that we recalculate the slant range to ground range conversion with higher accuracy. In our method, we suggest to first use some image processing on the backscatter image in order to find segments on that image, separating the highlights and the speckled seafloor. We use anisotropic diffusion and some filtering in order to arrive at a segmentation that we can use. Then, in the interferometric processing, we enforce that any averaging has to happen within the same segment as the current pixel of interest, and that segment has to be continuous. More details on the processing steps and the algorithms is available in the paper. First, we tested our method on a simulated flat seafloor with a small box 1 by 1 meters raised 25 centimeters above the surrounding seafloor. The axes in all the figures I'm showing are the same. They have the horizontal positions along track and across track in the x and y axis. The intensity, depth, or interferometric coherence are shown as the color-coded images. The red dashed line indicates the ground truth boundaries of the raised box. Here we show the bathymetry estimate from the default method. And the default method refers to the typical averaging using a square window. It shows clearly the effect of smothering the edges and yielding the wrong bathymetry estimates. In addition, we can see that the wrong bathymetry estimates actually have high interferometric coherence. The interferometric coherence is a measure of signal quality, or signal-to-noise ratio. And it is high in this case because of the inclusion of the strong scatterers from the object. This is misleading, as we usually trust the interferometric coherence with high confidence in telling us the quality of the estimates. Comparing the default method in the left panel with our suggested method in the right panels, we see that the edges are now preserved. We can see the layover region now appearing in front of the object, and the shadow region is visible in the bathymetry as well. It's not perfect because our segmentation method was made simple by design and does not sort out shadow from seafloor. So therefore it will do some averaging across the speckled seafloor and the shadow. Since we also do geometric correction of the initial SAS image after estimating the bathymetry, we also get an improvement in the sharpness of the SAS image. For example, comparing the speckled seafloor right in front of the object, we can see that it looks defocused and stretched in the default case, while it looks more like the surrounding seafloor using our method. This is because of the improved bathymetry estimate. In fact, we have 5.5% more samples with our method that have less than 10 centimeters difference from the ground truth. But still, the main advantage is the more precise rendering of the object edges. Here we have an example of real sonar data with a 10 by 10 meter image containing a few protruding objects, indicated by the red dashed lines. Notice that the red dashed lines here just highlight the rough position of the interesting objects. Here we show the bathymetry estimates. Again, the default method is in the left panel and our suggested method on the right. We find much of the same as with the simulations when examining these up close. Looking closer at one of them, we again see that the default method estimates the object in the bathymetry to be much larger than what we would expect from looking at the backscatter image. Again, our method improves this and enforces the edges found in the backscatter image. We get an improved shadow region, and the layover region is rendered plausibly. The dark blue spots of missing data is due to some filtering on very low coherence values and the geometric correction, so that we don't show any data in ground range positions where we don't actually have any data due to layover. Looking closely, we can also see that the sonar image looks to be more focused with our method, and the coherence is even slightly higher on the object because we have excluded the surrounding seafloor samples. So to sum up, we have proposed a method to use features from the backscatter image in the interferometric SAS processing in order to improve the bathymetry estimate. We demonstrated our method on simulated and real data, and we found that we got the improved edge preservation, we got more correct bathymetry estimates, we got sharper SAS images after the geometric correction, and we also got slightly improved interferometric coherence. There are some concerns that I mentioned in the paper, but the main concern is the fact that we are heavily reliant on the performance of the image segmentation. So if the segmentation algorithm does not perform well, then the rest of the method cannot perform well either. So future work should really deal with making this robust and making sure that it works on most different types of seafloor and objects. And that concludes my talk. Thank you very much for your time, and feel free to send me any questions that you may have if you haven't already. Thank you, bye bye.